In the sum of products design method, we can design circuits, which means to come up with a Boolean expression if we just know the truth table. So when we talk about sum of products refers to both a design method and a first is a design method, and another one is a type of equation. So right now I'm talking about the design method called sum of products. So we can look at just a truth table and we can come up with an expression. And the type of equation is called the sum of products form. So the expression that we're going to come up with the sum of products method will be in the sum of products form. So I know that sounds a little bit confusing, but bear with me and I'll show you what I mean. Let's use the sum of products method. And the steps are as follows. First, we make a truth table, then we figure out the outputs that are 1, and then we write products for them, and then we OR all the products together, and that gives us our sum of products expression. So it's best to learn sum of products by doing an example. In this example, I'm asking you to design a logic circuit that has 3 inputs, A, B, and C. The output shall be high when the majority of the inputs are high. So the solution. And I also posted this for you. This comes from the Talkie textbook, and it is solved in full in a document that I posted for you called Practice Problems, Sum of Products. So to solve this problem, first we need a truth table. I did say that it has 3 inputs, A, B, C. Since there are 3 inputs, then there must be 2 to the n, where n equals 3 lines on the truth table. So that's 2 to the power of 3, which is 2 times 2 times 2, which is 8 lines in my truth table. If there's 8 lines in my truth table, then 4 of them must start with zeros, and 4 of them must start with ones. So there's my truth table. And if you don't know how I filled in this truth table by doing half zeros, half ones, and then going half again, half zeros, half ones, half again, half zeros, half ones, then I need you to go back to lecture 1 and refer to that. So, but that's the way you fill in a truth table so that you know that you have all of the entries. Now the question says the outputs shall be high, which is 1, when the majority of the inputs are high. So the majority of the inputs are high here. So the output's 1. Majority of the inputs means 2 out of 3. So this is 1, this is 1, this is 1. I believe, is that all? Majority of the inputs are high. Okay. So this looks like a reasonable truth table. The rest of them must be low because the majority of the inputs are not high. So first I obtained that truth table by looking at the question. Now, so that's step 1. And now I'll do step 2 in a different color. Step 2 is I'm going to figure out where there are ones, where the answer is 1. The output is 1. And I'm going to write the product for each case where the output is 1. Now, what do I mean by writing the product? I write the product, which looks like it's going through an AND gate, right? It's going through an AND gate. it looks like they're multiplied together. That's what product means. So the products are A, B, C for each of these. And this is step 2. Step 2. And now write down the products and look at if there's a 0, then invert the A. If there's a 0 here, there's a 0 on B, so I'm going to invert that one. Here's a 0 on C, and I'm going to invert that one. So that's easy enough for you to do, but it might beg the question, why am I doing that? And if you really want to know why, it's very well described in a document that I posted for you called Practice Problem Sum of Products. It proves why this method actually works. So that's step 2. Step 3, I'm going to write in blue, says that I should OR all the products together. So here's my products. There's my products. And I want to OR them all together. So that looks like this plus sign, right? Step 3. And sum of products design method is not a difficult method. And there you go. That's the answer. So what have you come up with now? What you've come up with is you have said, if this is my truth table, then this is the Boolean expression that defines the logic in this truth table. That's pretty neat, isn't it? Step 4, it says to simplify the expression. So I'm going to write that down, that expression down again. Here's the expression that represents the truth table. And step 4, what should I put that in? I'll put that in red. And this will be good practice for us, simplifying. I'm going to use that trick that I've used before where I recognize that I can use a theorem where I can add another ABC plus ABC, and then I'm going to regroup those. I can add as many ABCs as you want. If you don't know what I'm talking about, then take a look at the synchronous class where it's week 5 synchronous class where I prove that I can add as many of these terms as I want to, because y or y equals y, one of our theorems. So there's our original equation with the extra ABCs added. And what that lets us do is recognize that we can take out factors BC plus from here factors AC plus from here factors, let's see, AB. And conveniently that leaves me with these expressions, A prime plus A, B prime plus B, and C prime or C. And those we know in our theorem turn to 1. So now this is BC or 1 plus AC or 1 plus AB or, and 1. And anything ANDed with a 1 is going to be the same as just that thing itself. And I can't see any further way to simplify this, so I'm going to say this is the answer. Simplified. So what have we done here? We've taken the description saying output is high only when the majority of inputs are high. We were able to generate this truth table. From this truth table, we were able to say, well, this is a Boolean expression that governs the truth table. I was easily able to come up with that by doing sum of products forms, which just means that I sum up the products that I took from the truth table where the outputs are 1. And then I simplified that expression and I said, well, if I build this, then it will behave like this. And that's the sum of product form. That's the sum of product design method.